Hello everyone, this is Tiger again. I haven't seen you in a while, so I am actually quite missing you there. Well, let's cut it short and we will get started with today's session, and it will be the explanation on 2019 JMC, and this is the first half of the paper. Are you all ready? So let's take a look at the first question. And clearly, it's going to be a word problem on time. So, problem. And it's going to be a time problem. How many minutes is it from 23:35 today to 1:15 a.m. tomorrow? Well, clearly this is written in the 24-hour clock. So we can just try to cut it up into sections. First of all, we think about how many minutes is it from 23:35 to midnight, which is 0 o'clock. And then think about how many minutes is it from 0 o'clock to 1:15. So clearly that span is going to be 25 minutes. And the second one, we have 1 hour and 15 minutes. So that's going to be 60 adding 15, which is equal to 75 minutes. Clearly there's 60 minutes in an hour, right? So altogether we have 25 adding 75, which is 100 minutes. And the answer is going to be A, okay? So that's for the first question, pretty simple. And for the second question, it is a numbers and operations question. So numbers and operations. Well, you can say that it's about decimals, or you can say that it's actually a bitmas question. So we just need to know which to calculate first. Definitely what's within the brackets. So if I have 0.1 adding 0.2 adding 0.3, take away 0.4, what I have is 0.2, right? Because those are going to cancel out with each other. 1 adding 3 is 4. And then I am dividing that by 0.5. Which means that actually I have 2 divided by 5. So there are two ways you can solve it. First of all is just simply do the division. So you have 2 divided by 5. Well, we know that's going to be 0, but we don't want the remainder. So we add a 0 after the decimal point, and 5 times 4 is 20. So we know that is going to be 0.4. Or we can also write it as a fraction, 2/5, and you know that's going to be 0.4, okay? So those are the two ways that you can solve it. That's for question 2. Moving on to question 3, it says Sam has eaten 3/4 of the grapes. What is the ratio of the numbers of grapes that remaining to this number that Sam has eaten? So that's a word problem on ratios. Well, if Sam has eaten 3/4 of the grapes, it means that that's going to be 3/4 grapes, which means that what remains is going to be 1 take away 3/4, because we can treat 1 whole as a fractional 1, right? So that's going to be 1/4 of the grapes. So if I want to find that ratio of remain to eaten, that's going to be 1/4 to 3/4, which we know that for a ratio, if I want to find the equivalent ratio of it, I can do the same operation of multiplication or division on both sides of the, like the colons, the ratio sign. So we can do times 4 on both sides. That's going to be 1 times 4 on that side. That's going to be 3. So it's equal to 1 to 3. And that's going to be the answer for the third question. Okay, moving on to the fourth one. So which of these following shapes can be cut into 4 pieces by a single straight cut? I would say that it's a geometry question on splitting. Well, basically it's also a little bit related to spatial recognition, but then how we are able to get the most number of cuts, basically, it's by, well, removing as many loose ends as we can, right? For example, you can see that A has got 2 loose ends popping out without connecting together, yeah? So we can do a cut right there to cut it into 3 pieces. But for B, since that the whole thing is a whole, like, they are all connected to each other without any loose ends. So there's no way I can cut it into 3 pieces, right? So I can do 2 only. And as for C, there are 2 loose ends, so we can cut it into 3 pieces. As for D, again, no matter how I cut it, I can only get 2 pieces. For E, however, it has got 3 loose ends, so I can cut it into 4 pieces like that. That's why the answer is going to be E, okay? But of course, there are some special cases. For example, like I, even if it has 4 loose ends, you can only choose to cut on one side of it. Well, because like each straight line can only go through 2 of them. There's no straight line that can go through 3 or more of these loose ends. Even if you cut it like that, that's going to be 4 pieces. But that's another story. Okay, so the key is to try to remove as many loose ends as we can. Okay, that's how it works. And the next one, question 5. So it is a very typical age problem, and I would say it's a pretty easy one as well. Basically, it says that on Alfie's 16th birthday, Buster was 3 times her age. So let's say A and B. When A is 16, B is 16 times 3, which is 48 years old. And when Alfie is 21, it means that 5 years have passed, which means that 5 years has also passed for Buster. And Buster is going to be 48 adding 3, that's 53 years old. So the answer is going to be C for question 5. And then for question 6, this is just simply a calculation problem. Which of these is closest to 7? So it belongs to numbers and operations. And this time it is definitely related to decimals, so the calculation of decimals. So the first one, take away 7, because this is greater than 7, so I'm taking away 7 from it to find the difference, which is 0.09. The second one, 7 take away 6.918, that's going to be 0.082. The third one, the difference is 0.17. The fourth one, 0.3. The fifth one, 0.085. So now you just need to compare the 5 differences and see which one of them is the smallest. The smallest difference means that it is definitely going to be the closest to number 7, right? So the smallest one, 0.082, corresponds to B. So B is going to be the answer for question number 6, okay? So that's it for question 6. And for question 7, so it is again a word problem. It is kind of wordy, but then basically all we need to do here is extremely simple. It is a word problem on multiples. So like questions related to multiples. Basically it is just asking you how many times longer is 7,821 than 2.06 meters, and the last one was in kilometers. So we just do 7,821 kilometers divided by 2.06 meters, which definitely they are not the same unit, so you can't calculate them right now. You need to convert them into the same unit. So that's roughly 8,000 kilometers, which is 8,000 meters, right? Which is 8 million meters. and that's roughly 2 meters. So now I have them in the same unit, meters, which means I can remove them. So it's going to be equal to 4 million. Just count the number of zeros right, using the separators if you want to help you count the number of zeros, and the answer is going to be the first one with 6 zeros behind it, representing 4 million. So that's the answer. And for question 8, okay, I'm just going to put my hat here now. So for question 8, first of all, there are actually many ways to solve it. You can either use the interior sum, like the interior angle sum of quadrilaterals, or you can also make use of the co-interior angles of parallel lines if you recognize that rhombuses have parallel sides, like parallel opposite sides. But no matter what, this is going to be a geometry question on angles. So if you're making use of the co-interior angles, it means that this angle and 120 degrees adds up to 180 degrees, because they are co-interior angles with SR and PQ being parallel. So this one is 180, take away 120, that is 60 degrees. And I'm talking about angle SPQ, Q, which is the vertex, the angle of the rhombus, the other angle of the rhombus. And now we can try to see that, well, this angle is going to be equal to this angle because they all have 120 and 35 as the other two angles in the triangle, right? So by the interior angle sum of the triangles being 180 degrees, each of them is going to be, so SPF equals angle QPG, and each of them is going to be equal to 180, take away 120, take away 35, so that is going to be 25, which means that the remaining angle FPG is going to be equal to 60 degrees removing 2 of these 25s. So 60 take away 25 degrees times 2 is 10 degrees, and that's equal to the angle FPG. Okay, so the answer is A for 10. Of course, you can also solve it by the interior angle sum of the quadrilaterals, which means that once you know that the opposite angles of the rhombuses are the same, you can figure that out. That's for the last question. And for question 9, this is actually a very interesting question because it is making use of an interesting property of percentages. So I would say it's kind of a word problem because it's not directly giving you the operations there, and it's going to be on percentages. We know that percentages are essentially just a fraction, right? And fractions are essentially just division. So basically 50% of 18.3 is 50% times 18.3. Adding 18.3% of 50, which means 18.3% times 50. And we know that is actually just fractions, right? So we can convert them into fractions such that I have 50 divided by 100 times 18.3. Adding 18.3 divided by 100 times 50. And you can see that they are actually the same. So if you find the common multiplier between them, everything is a common multiplier. But how would you make it easier for us to calculate it? Which means that this is 50%, this is 50%. Altogether, that's going to add up to 100% of 18.3, isn't it? So we can effectively just try to cancel these out. And the answer is just going to be 18.3. So you can see that actually those can be interswapped. 50% of 18.3 equals 18.3% of 50. They are actually just the same. So it might be useful somewhere else. Just use your imagination when you encounter these kinds of problems. And then for question 10, it is a miscellany question on optimization, but then you need to understand what the question is asking you first. So it is asking you the last digit of the smallest positive integer whose digits add to 2019. Well, so you might be able to see that's going to be pretty much a large number, right? And I want to have the smallest such number. So we need to think about how we compare the sizes of the numbers. So when we're comparing numbers, the first step, of course, is always looking at whether it is positive or negative, right? And the second step is to compare their length, basically. So how many places do they have? Because like in this case, they are all positive integers, right? So the longer it is, the larger it is. The shorter it is, the smaller it is, definitely. If it is taking fewer places, it will be smaller. So it means that I want to look for as few digits as possible. But then we also know that all the digits add up to 2019 no matter what. Which means that if you want as few digits as possible, you want every single digit to be as large as possible, right? Think about it. If I have a 9, it is just having a sum of 9, right? Or if I have 9 of the ones, which is definitely going to be bigger of a number than 9, but it still adds up to 9. So it means that I need to take the largest digit possible, which is 9. Which means I need to take as many nines as possible. Now, I need to add up to 2019, which is not divisible by 9. So let's see how many 9s do we need there. And it's going to be 224 with a remainder of 3. Which means that I have 224 9s and a 3 in my number. So the next step where we try to compare the numbers is to put the smaller digit in front, right? When two numbers have the same number of digits and we try to compare them, of course, we look at each digit one by one. We compare each digit one by one, starting from the largest one. So definitely if I want the smallest possible integer, I need to put the 3 at the very beginning and with a bunch of 9s. Actually, like there's 224 of them. But anyhow, the last digit is going to be 9, right? So the answer is going to be E for 9. Does it make sense? So you need to be very clear about the logic when you're trying to compare the numbers, and that's how you can solve this question. All right, and the next one I need to hide myself for now. This is the miscellany problem on winning strategies, or you can say that it's an operational problem on winning strategies. So basically, it says that, well, now it is Y's move in one of these 5 figures. And after Y make his move or her move, Y wants X to lose the game. And the condition to lose the game is to make sure that the other one cannot put any numbers in that. But you can see that in each of them, there are 2 empty boxes, right? Which means that if Y put a number in one of them, X can put a number in the other. So how can you make sure that X cannot put any number into the remaining box? The only way is to make sure that 1, 2, or 3 are all invalid for that box, which means that that remaining box is connecting to all the 3 other numbers 1, 2, and 3. So which of the remaining boxes is connecting to 3 numbers? You can see that this one is the only one empty box connecting to 3 other boxes, because the 1 has already been filled, right? So the answer must be one of D, E, or A. We can eliminate B or C first. But then for A, you can see that we can definitely put a 3 in there, which means that X can definitely just try to put anything like a 3 in the remaining box, which means that A doesn't work because this can be a 3. I need that box to have, like, I need X to have nothing to put in that box, right? So for E, we can put a 3 there, like Y can put a 3 there, such that this box is connecting to all 1, 2, and 3, which means that X cannot put any number in there, right? So the answer should be D. As for E, you can see that the pattern is the same, but then the bottom number is a 3, which means that Y cannot put a 3 here, right? So if Y cannot put a 3 here, no matter it is 1 or 2 that Y is placing, X can always place a 3 in that box. So it means that Y has failed to limit X. So D is the only one to make sure that Y can win. Does that make sense? That's for question 11. And question 12 is suddenly becoming pretty easy once you understand what the question is talking about. So essentially, this is a numbers and operations problem. And you can also say that it's inverse operation, but then I prefer calling it the Fibonacci like sequences, because it actually is. In this sequence, each sum is the sum of the 3 previous terms. And I want to find the first term, so I just need to trace it all the way back. Now I have the 4th, 5th, and the 6th terms, right? So using the 6th term, subtracting 8 and 13, which are the previous 2 terms, I can find the 3rd previous term, right? So that's going to be 25 take away 8 take away 13, which is equal to 4. And then the second step is from 13, we can trace it back to this box with 4 and 8. So that is going to be 13 take away 8 take away 4, which is 1. And finally, using 8, I can trace back to that box. It is going to be 8 take away 1 take away 4, so the previous 2 numbers, and I got the remaining one, which is 3. So the answer is D, which is 3 for this question, okay? So that's question 12. And then for question 13, it is actually, I would say this is quite a complicated question if you don't know the marking method. But it is not really much a typical marking method question. However, we can still use the marking method if you know what it is. So basically, the marking method applies to everything, to any question that is involving counting the number of ways. When you are given some routes with fixed directions, So you can see that you can start from the center. You have to start from the center. Moving on to the next numbers, which are horizontally, vertically, or diagonally. Which means that starting from this J, we have one way of reaching this J, right? And then you can go to all the other 8 boxes around. And then we need to think about for each of these M's, how can you get to the C? So basically there are 2 types of M's. For the corner M's, there are 5 possible C's that it can get to. So those are for the corner M's. Maybe it's a little bit messy, but hopefully you know what I mean. So each corner M can go to 5 C's. And what about for each middle M? It can go to 3 C's. Oops. Suddenly my writing board is out of electricity. That's awkward. Well, maybe we have to wait a short while when it reconnects. But essentially what I mean is that each center M can go to 3 boxes, right? 1, 2, 3. And the others are just going to be the same. Each one can go to 3 boxes. So finally, what I can do is that you can either just try to start from the J and then count the number of ways you can move to the next step. So that's really messy right now. But then if you are really on a piece of paper, I believe you can draw a clearer picture than this. So starting from J, I have 1 way that I can get to J, right? And also I know that I have 8 ways to get to the M's around it. So that's J. Maybe I should use a different color. Say I should use green for J. And then so I know that there can only be 1 way I can get from J to each of the M's, right? But then for C's, you can see that for the corner C's, only the corner M's can get to them, right? So the corner C's have got 1 ways each, which means that I've got only 1 way to end with each corner J. And then for the side C's, well, they are the side or the middle side. Let's say the side. So you can either come from this box or this box, right? So there will be 2 ways for each of these side C's. So that's how we can deduce them. And for the center side C's, you can see that there will be 3 M's that can reach each of them, right? So we add the number of paths altogether, and you can see that's going to be 3's in each of them. So you just need to add the blue numbers all together because that's how you can reach all the C's, right? So we have 1, 2, 3, 2, 1, 2, 3, 2, 1, 2, 3, 2, 1, 2, 3, 2, which means I'm having 2, adding 3, adding 2, adding 1 times 4. That's going to be 8 times 4, which is 32. Or the other way is that you can just take a look at the 2 different types of M's, the corner M's or the middle M's. The middle M's can get 3 ways, the corner M's can go 5 ways, right? So 3 adding 5 multiplying 4, which is the number of corner M's and side M's. So 3 times 4 adding 5 times 4, that's also going to be 32. Okay? So that's basically question 13. As for question 14, this question is, again, kind of interesting. I would say it belongs to miscellany again. And it is the 7 bridges problem, kind of. The question says that we need to start at a vertex without visiting any, without revisiting any vertex, right? Which means that for each vertex that you're going through, there will be 2 paths joining to it. One way in and the other way out. For any vertex that has more than 2 paths, you need to abandon the extra ones. So we can see that in this diagram we have 3 vertices that have more than 2 paths. So for the shorter one, of course, I just need to abandon 1 path of it. And like for this one, we just need to abandon 1 path of it because there are only 3 paths joining this vertex, right? For the other 2, I need to abandon 2 paths each. So basically, we just need to decide which paths am I abandoning to know how many sides I can travel. So essentially, if I am abandoning, say, this path for this vertex, which means that I'm also abandoning 1 path for the top vertex, right? Because this is shared. So I want something to be shared, definitely, such that I can remove as few edges as possible. And then I'm removing this. And for the triangle, I have to remove both of them. Otherwise, if I remove this one, it won't be continuous. Or maybe if I put it this way, it might be a little bit hard to understand. The other way to understand it is that, well, essentially, you can just treat these extra bits as the dead ends. Because once you go through these vertices and you enter these dead ends, you can never come out of it again, right? And now we can see that there are 3 of these dead ends. One of them can serve as the start, and the other can serve as, like, in one of these dead ends, or the dead loops. One of them can serve as the beginning, and the other can serve as the end. So if I want the path to be as long as possible, I'm definitely choosing the longer ones, right? Which means I'm abandoning this short path. And because we can't revisit these vertices, so definitely I'm choosing a point that is away from the vertex. So I'm definitely not starting from the vertex. Otherwise, I will never be able to get into the loop again. So say I'm choosing these 2 points, and then I'm just trying to find a way that I can maximize the route. So definitely I'm taking the long way there, and then all the way down there, trying to travel as long as possible before I go into the triangle. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which is 10 centimeters. Okay, that's how it works. That's how it works. And finally, for question 15, basically we have 4 L shapes, and then it is asking you that how can all the 16 cells be covered without overlap, and how many of these 16 cells could contain the black dot. Well, we know that for each of these 4 pieces, there will be, well, like simply speaking, generally 2 different ways to arrange them. The first way is that I am putting all of them in a spiral way, such that it's kind of looking like the swastika, which is not really a good thing to know. But yeah, that's what's going to happen. And then the black dot is going to be one of these 4 center boxes, right? So it means that I can go into all the 4 center boxes. The black dot can be anywhere in the center cells. And then after talking about this arrangement, we actually, probably I'm just going to leave it there. We actually have another arrangement, which is like putting them in the L shapes. So 2 of them are going to form a group, and this is a 2x4 rectangle. And the other 2 can form another group on the other side, forming another 2x4 rectangle. So that's the other arrangement. And you can see that in the other arrangement, of course, you can rotate it or you can flip it, because we definitely know that a square is rotationally symmetrical of order 4, and it can be reflected as well. So you can see that the black dot is going to be either at the corners or on the sides, right? So altogether we have 8 side cells, which by rotation you can make these 2 black dots, or whatever it is, visit any of these 8 side cells we want, and also 4 corner cells. Again, by rotation you can make them locating in any of these corners you want. So essentially what we can see is that all of the 16 cells can contain the black dot. And this question is a geometry question on spatial recognition. Okay. Did I put down the notes for the previous ones? Oh yeah, I think I did. Okay, so that's everything for today's lesson. That's everything for today's session right there. If you have any problems, feel free to let me know. So I will see you next time on Thursday then. Bye bye.